in the last class, we discussed how to derive the classical equation motion. Basically, our starting point is that we have a phase space Lagrangian, which describe a quantum system. So the phase space Lagrangian have this form. Which actually is a function of this wave function per psi and its derivative, basically. So then, in the classical physics, to obtain the classical equation motion, somehow we obtain this some kind of corresponding phase space Lagrangian in some parameter space, a phase space. But this one is actually given by this. Formula is very similar to what we have above. Okay. So it looks like these two are the same thing. Why this is a quantum Schrödinger equation, this is a classical equation motion. And indeed, these two are very similar. In this case, this wave function is just any unit vector in the vector space. Hamiltonian, a quantum system is described by state in the vector space. And we have Hamiltonian act in the vector space. And the equation motion for the wave function actually can be written in terms of a Lagrangian form, where we have a unit vector in the vector space, so that's per psi. And then you can using this unit vector in vector space as your phase space labeling. Then you can obtain the equation motion moving inside this phase space. And to obtain its classical analog is that following. We no longer treat any unit vector in the vector space. We somehow select a subset of unit vector in the vector space, some small collection. Then we try to consider the motion inside this small collection, this subset. So that's how we do it. So this kind of per psi c is a subset of this unit vector. So basically, this is like a variational state, a trial wave function. And the c is our trial parameter. Okay. But usually when we're using trial wave function, we just want to find a value of parameter c to minimize ground state energy, to obtain the good ground state energy. That's how we use it. And here we use the trial wave function a different way. We say that our trial wave function is selected very smartly, so that the quantum motion at the low energy basically are described by different value of c. So basically we say, at the change value of c, this wave function not only describes ground state, but also describes some low-lying states. Then at the low energy, the motion wave function basically are captured by this function labeled by c. And then we want to obtain classical picture. You say, what is the classical motion if you treat the c as a point in the phase space, and how this wave function move in the phase space. And then that's such kind of classical motion are described by this like a projection of this Lagrangian. We restrict this Lagrangian to some subspace, and that's how we get it. And so as one application for this, let's consider a quantum system, a kind of harmonic oscillator. Okay. So how do you choose this trial wave function? So our choice of trial wave function basically is we have c1 and c2 have two parameters. which is given by this alpha square root of alpha pi over quarter and e to the I plus c2x and e to minus 1/2 alpha x minus c1 squared. So this is our choice of a tri-wave function. And so usually one may choose this one, some Gaussian. You know, have a Gaussian wave packed center at C1. So because this potential is some kind of like a harmonic potential, some potential well. So some Gaussian wave function would be very nice. That describe ground states. Okay. So this is the most natural thing to do. You want to do this. Okay. But there's a problem if you do this. Because if you do this, there's only one parameter. Yes? C2. Oh, yes. Maybe I should have put only up and down index. Okay. So, but this one have only one parameter. You know, usually in the phase space Lagrangian, we need 2 parameter. You know, one is coordinate, one is momentum. So one parameter is kind of inconvenient. But certainly you may insist on using one parameter to see what you get from here. I don't know, I didn't try, but you may get something very strange. Okay. And so we need another parameter. But the other parameter should be kind of like a dual or canonical conjugate of the first parameter. And in this case, it's kind of obvious. Because the first parameter basically describes the center mass of a wave packet. The canonical conjugate of a location should be momentum. So this is why we choose the second parameter as a momentum, a wave vector. And so there's some kind of dual, some kind of duality relation between these 2 parameters. And so this in this case is obvious, but in some other not so obvious case, one can follow similar way of thinking. You know, there's one parameter, another parameter is better to be dual. The reason is following: we not only want to obtain the ground state energy, we also want to see the motion of the parameter. To really capture the motion, we need something to shift it, to boost it. And the boost for the position is the momentum. The momentum, like a translation to the position. We translate. And so in general, we need this pair. You don't have to be exact. You know, if it's off a little bit, it's fine. But you better have something like that. Okay. Okay. So this is basically why we choose this parameter. Yes?
So projecting back to this is assuming your wave function will stay as a sum of a bunch of Gaussians whose width would stay the same.
Very good point.
Why not stick in something
Yeah.
to make the Gaussians spread?
Yeah. Maybe that's one of the, you can choose as a project. So it's very nice to say alpha can have a time dependent. We can choose alpha as dynamic variable. So wave pattern breathe. And now this challenge, what is a dual or conjugate for the alpha? It's a little bit challenging. I don't know, I haven't solved all of it, but so this will be something quite interesting to see. What is the proper conjugate of alpha? And yeah, I don't know. I can think about it. And then you do something better. You have alpha and beta. You have 4 parameters. You have not only have a motion of center mass, you have motion for breadth of a wave packet. And you may get a better result. Yeah. So yeah, so this is I don't know, yeah, this is yeah. We'll see whether this would work helpful or not. But anyway. so this is a, but once you set up this, then everything else is mathematics. Just plug in, you get results. Yeah. So the most difficult thing is to have some intuition, some idea how to set things up, how to choose properly these two parameters. Okay. So let's just, once we set it up, so let's just quickly do the math. And so formally this, let me just start from here. So if I do the calculation here, this one can be written as the following, as a AI, which is function of C, maybe J and C I dot, and some average Hamiltonian is function of C I. So this H bar is just this average, is a function of C. So, and so let me explain this a little bit. And this AI actually, you can see, this time derivative is goes through this C. Only C depends on time. So therefore, this AI is really given by I times there's some C dependence, but DD C, partial C. This is down there. AI is a vector in the C space. So it's just the overlap of wave function with the derivative respect to C. Just some kind of overlap. Okay. And once you know this derivative respect to C, then derivative respect to time just basically given by derivative of respect to C times the C dot. That's the kind of chain rule. Okay. So this is a phase-space Lagrangian. So therefore, you can see to derive phase-space Lagrangian, it's very important to calculate this term, the derivative respect to C, and with overlap. Okay. And this term have a interesting meaning. It's actually geometrical phase, or also called the Barry's phase. Yeah. So this term is related to the geometrical phase. So therefore, the phase-space Lagrangian have two terms. One term is very simple, just average energy, Hamiltonian. But the first term is what we call the px dot term. The px dot term in this case actually is a Barry's phase term or geometrical phase term. Have this interpretation. And this is the general structure of phase-space Lagrangian. This one will have a geometrical phase term and a Hamiltonian term. They together give us this phase-space Lagrangian. Why we call this a geometrical phase term? And so let's consider the following, just overlap of this C plus, no, just C I and C I plus some kind of delta C. Let's consider this overlap. This overlap just basically equal to 1 if delta C equal to 0. If delta C not equal to 0, this term basically is a pure phase term. It's a pure phase term. Why is pure phase term? Let me see. Okay, so because both wave functions are normalized, okay, and so it's like two vectors. They differ by a little bit. They differ by a little bit. But when we do the overlap, the absolute value overlap is like this projection of this vector to this. But this change of length is If this is delta, this change of length will be delta squared. So when you do the overlap, the change of the absolute value only changed by delta squared term, which is high order, so we ignore. We only keep linear order term. So if you keep only linear order term, the only thing that can change is a phase. So this is e to the I delta phi. This is a phase. And this is the proper definition of geometrical phase. That is, when you have a family of wave vector, you can do this overlap, consecutive overlap. And so you want to compare two states, two nearby states. But if the two states are very close, the only difference is the Barre's phase term. And then you can do the comparison, etc. Okay. So I will not go into Barre's phase term too much. Okay, so this is Barre's phase term. But from this point of view, you can see that if you expand this will be as a 1 plus I delta phi. Then clearly from this we can see that this delta phi is equal to, let me put the minus sign here. So that would be, so I can put I here. So delta phi will have this form. And written in what we use in terms of A will be like AI plus delta I. So that's why I say this AI describe geometrical phase. Because if you multiply AI by a small change of delta Ci, then this one is a phase of comparing two nearby states or coherent states. We call this a coherent state. So therefore, and this is very, I feel very good to realize this. The first term in the phase space, Lagrangian, actually have in quantum mechanics, it's kind of like a Barre's phase term. And the second term is just a total energy. So this Barre's phase term plus total energy capture the dynamics of the quantum system. So this is a very appealing. Yeah. And so for those who know some advantage called the symplectic structure, then I just want to make a comment that the phase space is really some kind of symplectic manifold with symplectic structure. And this one determines some kind of function in this symplectic manifold. And this Barre's phase term defines the symplectic structure. Once you have a symplectic structure and its function, you determine the phase space equation motion. So there's some mathematical way to say the same thing. Okay, so with this comment, so let's just plug in. Then if you plug in, using this to plug in, we find this A1 equal to 0 and A2 equal to minus C1. And this is easy to see. A1 means we make a derivative with respect to C1. If you do that, we'll bring down a factor x minus C1 factor. Then you need to do the integration. You have a Gaussian on one side, x minus C1, and another Gaussian on another side. When you do the overlap. But now you have this extra factor. And because this Gaussian wave function even is symmetric about C1, now you have some odd function about C1, so this integration gets equal to 0. So that's why we have nothing here. But however, for the A2 is derivative with respect to C2, and then you bring down an x. You just bring down an x when you respect to C2, bring down x. So you have something like you have some x here. Then you do this, you have psi and psi dagger, psi star. On both sides, you do this average. But this space is the average of x. And this wave packet is centered at C1. So its average position is C1. So this average of x is C1. So that's why you get this. C1, but with a minus sign. So there's some sign. Okay. And H bar will be, it's easy to understand. It's just an average energy. It's messy. Because we have a quartic term, it's pretty messy to compute. So let's just write down the answer. So we just 1/2 C2 squared plus 3 alpha plus 2 alpha squared V 4 alpha squared C1 squared plus 1/4 C1 to the 4th power plus 3 plus 4 alpha cube. That's it. Okay. So this is the result. So let's just understand what this result tells us. Okay. This term actually is like a variational energy. And when the Kc, certainly, actually the whole thing is variational energy. Okay. And we can see that this variational energy is minimized if both Kc1 and Kc2 equal to 0. Because the contribution from Kc1 and Kc2 are all positive. If Kc1 and Kc2 equal to 0, this one will be minimized. But however, it's also dependent on alpha. So we can choose a proper value of alpha to minimize this wave function further. So that means there's some particular alpha which really minimizes energy. So that wave packet have a lowest energy. Actually, we want to choose that alpha. So alpha is not arbitrary parameter. We want to choose alpha which minimizes this term. So that determines the size of the wave packet. Then Kc1, Kc2 just describe how this wave packet move around. Okay. How they move around, if you look at the energy, then you have a, say, remember Kc2 is like a momentum, Kc1 is like a coordinate. But it's not just what we say. It's really from this structure. Because A1 equals 0, A2 equals minus Kc1. So actually, this we have a term which is minus Kc1, Kc2 dot. We have this term. And this term is equal to Kc2, Kc1 dot plus or minus a total derivative of Kc1 times Kc2. And this is more standard form. This is like x dot, and Kc2 like a p. So this is a px dot term. So actually, you can read it off. So if I rewrite this a little bit, we see that this Barrow's phase term have this Kc2 times Kc1 dot. That means we can interpret Kc1 as coordinate, and Kc2 will be its canonical momentum. Now, because this Barrow's phase term has this standard form, p times x dot. So this is the reason why we say Kc2 is a momentum, Kc1 is a coordinate. But certainly, you can do this as well. You say Kc2 is coordinate, Kc1 minus Kc1 is a canonical momentum. It's okay, that's equally okay. But then interpretation will be a little bit different. So let's using the second interpretation. Okay. So then if you second interpretation, this term is very simple. This is like a p squared term. That's the kinetic energy, which is actually reproduce this term. Yes?
Is there a reason that you need to identify the p's and x's effectively beforehand? Because doesn't that formula give you a sort of canonical way to calculate the canonical formula?
Exactly, yeah.
So you could have realized that.
Yeah, you're totally right. Even this variable is very messy. It could be very messy. You know, A1, A2 can be arbitrary function of C. Then you can get a very messy canonical momentum, and then write this in terms of x and the p. Yeah. Okay. Yeah, you're totally right. And here you see, beyond here we have very simple things. So this term is kinetic energy, just like this. And this term is a potential energy. kind of like this, not exactly. And you can easily see the difference. First, in this case, you can see when v equal to 0, the spring tension will be 0. We have a pure, x to the 4th term. Not here. When the v equal to 0, even when v equal to 0, we still have a 3 alpha over 4 alpha squared. Alpha is not equal to infinite or 0. So even when v equal to 0, we still have a finite spring constant. So what that means? That means following. When v is 0, very small, this will describe oscillator which almost have 0 frequency because the potential at the bottom is very flat. The frequency of oscillation is very small, almost 0. But this is not the right picture in the quantum. If you do quantum physics properly, the wave packet have a finite size. Because wave packet have finite size, it fill this quadratic potential further. And it's indeed do not want to move around. So therefore, actually, the effective spring constant is finite. And that's quantum effect. Because in the classical physics, it's like a wave function, it's really delta function. So you only see this flat part. So certainly that's the frequency will be 0. But because quantum fluctuation, the wave packet is big. And then you see some effective spring constant. So this is that effect. And so therefore, so once you have this became a standard problem. It's really describe a modified harmonic oscillator. The spring constant is renormalized from the V to some combination like this. Yeah. So certainly, if V is very, very big, and the alpha term doesn't matter, so in large V limit, you can see this term approach this term. So this is this give you some idea, how to derive some kind of effective classical motion from a quantum system. And then we find the effective classical motion is similar to this what we expected, but with some kind of renormalization. And this correction is due to the quantum fluctuation. Okay, so this is just a very simple example. Yes.
How do you separate the constant term?
Oh, constant term is just some shift of energy. In class, if you only interested in the motion, this doesn't matter. But however, if you're interested in the total energy of the system, this matters. And in particular, we can see that the ground state energy is okay. So ground state energy is this constant term basically, which already include the 0-point motion contribution. But however, knowing constant term and knowing this spring constant, we even know the first excited energy. Usually it's hard to calculate because this is a harmonic oscillator. To calculate ground state or excited state, we had to diagonalize big matrix. And here we didn't do that. We say the ground state is this one, and the first excited is this one plus some frequency determined by this spring constant. There's a h bar omega. So actually we get an explicit expression for the first excited states. Basically, it's something like this. Okay, but certainly this is approximate. And but if you lecture notes, you can see that the numerical value is very close to exact results. So this is a pretty good way to calculate first excited states. And you can also try the second and third excited states. But when you get higher energy, things became less accurate. Yeah. So this demonstrates how this was used. And Okay, so with this kind of example, so let's consider what we really want to do. So remember, what we want to do is that we have some band. We have some kind of hopping Hamiltonian in the described in tight binding model. Okay, from this hopping Hamiltonian, and we obtain some kind of a dispersion relation. So this is just a one-band model, and we'll consider multi-band later. So where this Tn actually is equal to T. Let me see which way it goes. I plus N I. Because hopping only depends on its distance. So Tn is just how long it hops. Okay. So once you know there's a hopping Tn during its Fourier transformation, you get this dispersion relation, the energy level spectrum. So this is what we get in the first class. Okay. And so we want to really derive its motion. And because when you have arbitrary dispersion relation, we don't have a notion of a mass. Okay. So we cannot use Newton's law, F equal to ma. So we have some trouble to see how to understand the motion of a particle inside this periodic potential. And but now we can using this method we can do it. And the key point again is to using this to design a wave packet. So this is very similar. We can design a wave packet. So our wave packet definition is this. Some kind of normalization constant over 2 c squared. Some size, the c is like size of wave packet. Then e to the I, k dot, these two I are different, and this I is basis vector. Okay. So what we do is here is following. We just include this Gaussian factor. Remember, if you don't have this Gaussian factor, this is just plane wave. And this plane wave is the eigenstate of this Hamiltonian, whose eigenvalue is epsilon k. Okay. But the plane wave have no center mass location. There's no position. So what we do is that we multiply a Gaussian factor to this plane wave. So this plane wave is a non-zero only near x, and the decay away, with at the length scale c. C is the size of wave packet. So another way to look at this wave packet is that this wave packet is superposition plane wave with momentum near k. The spread of momentum delta k is of order 1 over c. It's a 1 over size of wave packet. Yeah. So that's kind of a picture of this wave packet. And this k and x, it became our variational parameter, or parameter for the coherent states. And then we want to, using this wave packet, to plug in there to see what is the phase space Lagrangian and what is the motion. And that's it. So that's how we understand the motion. So basically, we construct wave packet in the vector space, and we say how the wave packet move around. And usually you will say that the wave packet will spread as it move around. So this c will become bigger and bigger. And but however, in this case, obviously we ignore the spreading of c. We can't assume the wave packet move around without changing the shape. And so that's kind of approximation we did here. Okay. So once we have this, then we can just do the math. So the most important thing is to construct some kind of physical coherent states. So from there, we can review the classical motion. And before I really do the math, I want to generalize this a little bit to include a potential term. So this I really have a vector in it. So this term is I is diagonal. So the coefficient tell us at this I side I have energy plus phi. Usually I assume, before I assume every side have same energy 0. So now I assume different sides may have a different starting energy. And then we have hopping between different sides. So we add some potential energy term for each side. Okay. So then we can just do the same calculation, try to plug in. So this looks like a very hard calculation, but actually it's a very simple calculation. So let me just write it. So let's do this calculation first. When I can write down this is equal to x times k dot. Sorry. You see, this is so quick. You mean, why is so simple? This is pretty messy here. So actually, this is pretty simple. You can really see that. The reason is following. When you do this derivative respect to t, you can see the t is contained in the k and x. So therefore, this term contains a derivative respect to k and a derivative respect to x. So when you have a derivative respect to k, then derivative respect to k bring down I. That's the location I here. Bring that down. And then when you consider this overlap, then you get essentially get something like I, but then you have the wave function, e to the minus 1/2 c squared, I minus x squared. And then there's another part, a Gaussian on the side. Sorry, I minus x squared. So this is like a psi, this is like a psi star. And you have something in between I. Take its average. The same thing is this wave packet centered at x. So average of I just gives you x. And certainly this is coming from derivative respect to k. So then we have in the chain rule, so we have x and k dot. So that's why I have something like that. And but there's another term with derivative respect to x. When you have a derivative respect to x, then you bring down something like I minus x. And then something like I minus x here. You do the average integration over I. Again, this wave packet centered at x, and this one is odd, about x. So this average is equal to 0 in this case. So that's why we don't have this. We don't have the other term. There should have something with x dot, but this term is 0, so we don't have that. Okay, so that's it. And then we have a term kx. This is a hopping Hamiltonian. Okay. Oh, this is hard. This is very difficult to calculate. Because hopping Hamiltonian is this part. So this part is a H hop. Then you have this messy wave function and want to calculate h hop. That certainly is difficult. But however, here we make an approximation. We say Kc is pretty big. You know, if a Kc is infinite, this is a plane wave. Then this average is very easy to do. This is just epsilon k. If a Kc is infinite, this is an eigenstate. So that's it. But Kc is not infinite. Kc is finite. If Kc is finite, that means k has some uncertainty here. So there's some error. But the error would be something like partial epsilon partial k times delta k. Something of that order, you know. But delta k is of order 1 over Kc. Okay. So basically, we say that. So let's consider we have this kind of spectrum. Epsilon k is like this. If 1 over Kc is a delta k, it's a small, so that's, you know, we can ignore this kind of change. So there's some ambiguity, some approximate. If we say, oh, in this place, this roughly just epsilon k is with some small errors. And so this is what we do. We say, okay, we say it's approximately it's epsilon k. There's no such term. Okay, that's pretty simple. And then we have this the potential term. So let's call this phi term. So we have we make life harder, so we add a potential term. So what is this? You say, oh, this is must be very difficult because we have some average of this potential using Gaussian wave packet, and the Kc is very big, so we average over a large area. And here we make another approximation. We say this potential is smooth, very, very smooth. Means even smoother at the scale of Kc. Kc is very big. But we say at the scale of Kc, the potential almost don't change. So it's very, very smooth. And so in that limit, the potential almost constant term in the region wave packet. So this average is just equal to this constant. It's just equal to phi, which may depend on the x, actually. So that's it. So from here, we immediately see that the phase space Lagrangian is just collecting all those terms. It became L equal to k plus x dot minus epsilon k and phi x. And certainly here, I kind of ignore this total derivative term, x dot k. Because this term is x times k dot. I kind of convert this into k times x dot, but differ by some total time derivative term, which we kind of throw away. Okay, so this is the phase space Lagrangian, which control the motion of this wave packet. Okay, so now we have a classical picture. The classical picture, then the equation motion from this will be like k dot equal to minus partial phi partial x, and x dot equal to partial epsilon partial k. So this is and this equation is very familiar because k is kind of like a momentum. So momentum, time derivative momentum equal to force. Partial phi partial x is a force. Okay. You know, actually, I skipped here. Actually, you can derive from here to here. I didn't do it, but it's straightforward because plug in this Lagrangian equation, you can get this result. So I won't do that. And this term actually is interesting. This term is generalization of a momentum velocity relation. In Newton's equation, we should have something like x dot equal to p over m. You know, Newton particle have a mass m. The p over m is a velocity. So we should have something like this. Or in our notation should be the k over m because k is p. But indeed, if this epsilon equal to 1/2 m k squared, so if this epsilon have this kind of a standard dispersion relation, this equation will become the standard one, velocity equal to p over m. But this relation is generalized. It became velocity equal to derivative of a partial epsilon partial k. It's still a function of k, but it's a complicated function of k. No longer, it's not like a velocity proportional to momentum. It's a velocity, it's a function of momentum, but it can be complicated functions. And that's it. With this generalization, we get these results. Okay. Yes?
I was wondering, you probably want to side directions. So what is the length scale we should compare to determine?
So the thing is that, so there's several things. Say this C should be much bigger than the lattice constant. That's a separation between two lattice points. And then the C should be much smaller than L phi, let's call this. The L phi is the length scale where phi has some significant change. So we say phi is very, very smooth. You know, at a large scale C, phi almost constant. So in this limit, this would work. Otherwise, things would be complicated. Otherwise, we are using some average phi, using this Gaussian average phi here as effective potential. Okay. So this is let me see. Okay, this is a motion. And this motion actually is very interesting. Let's just describe one particular solution. Suppose in one dimension, remember in one dimension tight binding model, we have some kind of dispersion relation like this. So this is a epsilon k. This is a minus pi to pi. Okay. Yes?
So the characteristic length here is much bigger than the lattice spacing.
Yes.
But also much smaller than the length scale of the potential.
Yes.
But isn't the
length scale potential actually says the potential is what is length scale potential? Suppose potential like this. We say okay, the potential have a significant change during this length scale. So that's all L phi. No, not that. It's just that's how they vary in space. It's almost constant on every side. But it's a vary over large scale. Then the lattice spacing is like this. So this is the lattice spacing. And our wave packet is this size. so that's how the scale was separated. And only in this case this kind of description works. Otherwise, the distribution is a bad approximation. Yes?
So do we break the translation symmetry by doing this?
Oh yeah, we break translation symmetry. When we have a potential, we break translation symmetry. So actually that's why we want to include this first term. You know, if I don't include the phi, then the k dot will be constant. So momentum will be conserved. But when you break translation invariance, you add the phi, then the k dot is not equal to 0. Momentum is not conserved.
What's the motivation for adding a phi I? I mean, in material, we don't expect there to be position-dependent potential.
The things are, we have perfect crystal, phi is constant, so we don't need that. But then the particle inside this perfect crystal don't move. And we want to describe the motion, we want to push them to move around. And we including phi, this phi is our push, you know, try to push them around. They're like an electric field. Yeah. So we can see how actually I'm going to describe how we push things around. Suppose we have a constant electric field. When you have a constant electric field, this potential like a linear, at least in some region. Okay, so how particle move under constant influence electric field? Also, it's very easy, very simple. When you push the particle continuously, the particle would keep accelerating. The velocity getting higher and higher and higher indefinitely. Well, that's not true for this case. Because as you push this particle, its momentum increase linearly in time and increase indefinitely with time. So the momentum would go from here, the next moment to here, to here, to here, to here. The momentum just go. But the point is that when the momentum reaches the pi and the minus pi is the same thing. So this momentum live on a circle. So it's kind of go back. So momentum kind of then go back to pi and minus pi same. So it kind of jump to here, just like unclock process, we say. Then when still increase. So momentum just keep increasing like this. It's a circle, so you can do that over and over again. But what is the velocity? Velocity is the slope of dispersion relation. That's what they tell us. This is the key. The velocity is a slope of a dispersion relation. So here, velocity equal to 0. So as function of time, initially velocity equal to 0. Then as you push it, velocity would increase. And increase, when you reach to here, the velocity reaches maximum, actually. When you push it further, something funny happens. The slope starts to decrease, so velocity getting smaller. And reach 0. Actually, this should be linearly grow. And reach 0, we'll reach the zone boundary. And we're still pushing further. But then we do too much a good thing. The velocities go in opposite direction against our push. And then back to 0 from a full circle. So basically, as you push electron in the lattice, the velocity sometimes go forward, sometimes go backward, sometimes go forward, sometimes go back. It oscillates. So we generate oscillating currents. And so that is what the equation motion tells us. And certainly this is not what happened in the material. And so that's something very puzzling. But anyway, this is the truth, actually. So if you really do this, this could happen, but not in the real material. In the real material, there's another effect, so that this don't happen. So so the other effect is a friction. So here I describe the motion of a particle without friction. Indeed, without friction, if you don't have a friction, then when you try to apply electric field to the crystal, the electron in the crystal would oscillate. And usually the friction is pretty big, electric field is pretty small. So we can hardly create a situation where electric field dominates effect of friction. So the effect we observe in the traditional solid is a friction dominated. So it's different from what he described here. But however, when you create some very perfect solid with a very little friction, apply very strong electric field, you can indeed observe this oscillation currents. Yeah. So this is so this kind of strange motion of a particle inside a solid. Yeah. So any question here? Yes. It's really just this, the how k, the time scale for k to increase from minus pi to pi. That's one period. And so it depends on this, but this depends on electric field. They do not depend on system size. Yeah. And here I want to say the following. In this picture, I only consider one particle in the band, or maybe a few particles in the band. There are situations, I think next week, you'll hear that we can feel the band, that's different situation. And when you feel the band, Okay, maybe let me just mention this a little bit because we are going to discuss it later. So what we describe here, we have just a few particles near the band bottom. And then when you push it, this particle just moving around. Because K keep increasing, this particle just move in a band and go back just like this. But remember, this energy band are just those energy levels. Those are just energy levels. When you have many fermions, the two fermions cannot, let's consider spinless fermion, just for simplicity. The two fermions cannot occupy same energy level. So when you have two fermions, we have to be one here, another one must be here. When you have many fermions, then you may occupy more levels. Remember, number of level, the number of level equal to n. N is the number of sites. That we did the counting. The number of level in this band is equal to number of sites. However, if a number of electrons equal to number of sites, so if you have one electron per site, then every level is a field. Okay. In that case, when you apply electric field, push it, every electron would move in the same rate. The K just move around. But however, no matter how they move, you always get the same state back. The state is every level is filled. So therefore, this pushing, changing K don't do anything. Don't generate any current in particular, because the current is an average velocity. When you fill the band, average velocity equals 0. When you're shifting K, average velocity still equal to 0. This is different from partially filled band. When you have partially filled band, when you push it, this K would shift from here to here. Originally, this velocity is very small. Now, velocity is very big. But when you have filled band, when you try to moving K around, you still have a filled band. Nothing changes. You still have 0 velocity. So the partially filled band is a metal, filled band is an insulator. So that's why we have sometimes we have metal, sometimes we have an insulator. Once we have a filled band, we have an insulator. If the band is not totally filled, we have a metal. And this can be seen from here. So that's can explain the metal and insulator. So other questions? Yes?
The right picture that I'm on, I guess we're talking about a ring structure, that's why you basically end up getting your drilling zone. And these K and the X.
Yeah, K live on the ring, so that's key. The K live on the ring.
Right. Well, we had a lattice. That was a ring as well.
Okay, lattice is also a ring. Yes.
The lattice is a ring. So now these K and the X's, they correspond to the centers of these Gaussian.
Exactly. Yeah.
K is how this.
K is like an average momentum. Now here the momentum, the velocity is different. It's quite different. In the Newton's case, momentum velocity just different by a constant, m. And here they can be quite different.
When you say one particle, you mean one of these Gaussian packets corresponding to one electron.
Yeah, exactly. I'm thinking of when I say one particle, I'm really thinking of just one electron in the whole system. But when you have a few electrons, they don't interfere. So I can, using one electron picture, then just add their effect. But when you have many, many electrons, the things became a little more complicated. They may interfere because the Pauli principle may take effect. And then we may have a picture filled band. Then the picture is different. Then we get the insulator.
You expanded about the minimum of that dispersion relation.
I mean, if you keep piling these things, the energy will not be no longer. So
Right. So that's why we don't see this effect very easily. Because when you push it, the energy of electron becomes very high. They are very unhappy to stay there. They want to find a way to lose their energy, coming back to here. That is the friction. So the friction is trying to move things back to the minimum. and the pushing, try to push it over this hill. If you push really hard, and the electron quickly get to the top before it's losing its energy, you can push it over the top, then you get oscillation. That's really the picture. But usually in the material, electron losing the energy very efficiently. They can when you push a little bit away from minimal, it quickly go back to minimal. And you push them away, you go back to minimal. This competition makes this wave pattern slightly deviated from the bottom. So that you get currents, but constant current, not oscillating currents. But if you really push really, really hard, you can go over the top, then you get oscillating currents. So that is that's a cool part of this this motion in the band. But usually it's very hard to reach that limit where you can push over the top. Yeah. Okay. So far we described the motion electron in a band. And actually this picture is pretty similar to Newton's picture. Yeah. And it's just the velocity as a function of momentum is changed from velocity as a proportional momentum to velocity can be an arbitrary function of a momentum. So this is generalization. In the next, I want to say this is not enough. In a single band picture, yes, this is okay. We derive this. But actually, when you have a multi-band, when you have several, like in graphene, there's another effect which is overlooked here. So this equation is not quite correct. There's some missing terms. And this missing term will appear in multi-band picture like graphene you studied. So the Newton's equation got further modified and in the band. So in next we're going to study this further modification of a Newton's equation. Yeah. So this may make one wonder, you know. Newton's equation not just equation, it's a law, you know. And then we say it's not true in a semiconductor. Then we wonder why it's true in a vacuum, why it's true in nature. You know, maybe our nature is one big semiconductor. And we might see these additional corrections. And you may see, we don't see, yeah. So actually we do see this correction. This correction has been discussed before. Because in a relativistic quantum mechanics, the energy is not square. Its energy is something like mc squared plus c squared p squared. I think something like that. Yes. So this is a dispersion relation for energy for the relativistic particle. So therefore, this kind of correction had been already observed. But there's yet another correction, and so let's discuss the other correction. So to understand the other correction, another effect, so we need to go to multi-band picture. So when you have a multi-band, so let's just review a little bit. So what do we have? In the multi-band, the hopping Hamiltonian is just equal to this Tij AB, and we're using I and A to label a site, and GIB to label a site, because each unit cell may have several sites. And then we construct some kind of matrix we call the MK with an index is AB. And this matrix basically is a Fourier transformation of this hopping matrix, TAB. N is a distance hop. And then we do this Fourier transformation. And let me see. Yeah, e to the minus n dot k. N is a vector, so all these are vectors. Okay, so this is a matrix. Once you know this matrix, we find that the Hamiltonian can be written in the k basis. this K basis is a Ka basis is a sum over e to the I K J J A, sum over J. So we go to the K basis. Using the K basis, so there's 1 over square root of n here. Okay. In the K basis, then the Hamiltonian became simpler. It became with sum over K, and this MK AB Okay, so in the K basis, it's almost like hopping Hamiltonian. You know, this Hamiltonian means JB can hop to IA, can hop around. If you change your basis, it's also like hopping. KB can hop to KA with a hopping matrix amplitude is just given by this MK, which is Fourier transformation for T. And the simplification we get is that K no longer changes. K is fixed. So we will have hopping between A and B index. So if each unit cell have only 2 sites, so this one just hop between 2 sites or 2 states. So it's 2 by 2 matrix. So therefore we can diagonalize this Hamiltonian by diagonalize this 2 by 2 matrix or 3 by 3 matrix if there are 3 sites per unit cell. And that's become much simpler problem. Okay. And if you do that, we find that the eigenstates, so this is a basis, but the eigenstates of this 2 by 2 Hamiltonian or the Hamiltonian is labeled by K and alpha, which is given by this kind of plane wave, e to the I K J, and we have this a wave function, this phi alpha K. And we sum over J and A. Sorry, this is alpha. This is wave function have A component. Yes. And the notation is that this MK AB, when you multiply this psi alpha K with it's a B component, you became epsilon alpha K psi alpha K with A component. I'm sorry about this, all this messy mess. And basically, so let me write this in a more compact form. So this just column vector labeled by this index B. And this is a matrix. So using matrix notation, just this M times this column vector, and which gave us another same column vector back. It's eigenstates, but with the coefficient epsilon. Yeah. And we can do that for every point of K. You know, K is just some label. For every K, we just have matrix. Then for every K, we can have a column vector. They can diagonalize the matrix. We get this. But because this matrix is some kind of like a 2 by 2, 3 by 3 matrix, so it has several eigenvalues and have several eigenvectors. So this alpha just label this a different eigenvalue and eigenvector. Okay. So therefore we have the band structure is we have several band. You know, this band and that band and etc. So this may be like alpha equal to 1, this alpha equal to 2. You know, so this will be epsilon 1, epsilon 2k, this is like epsilon 1k. So then for every choice of k, we have this eigenvalue here. These 2 eigenvalues for every fixed k is determined by this particular matrix at that k. That k and at each point we also have the eigenvector. For this band, we have 1 eigenvector. This band have another eigenvector, which is a wave function. So that's kind of picture of multi-band. Okay. Then something new happens is following. You can see Actually, each point not only have an energy eigenvalue, but also have some kind of eigenvector. So let's use this arrow to describe the eigenvector. Those have some eigenvectors, which is given by this psi k. This column vector is eigenvector. Then something interesting happens because as you shift the k around, because when you push it, the k would move around. And here, the eigenvector and that eigenvector may not be parallel. It may twist by the angle. And here, the eigenvector may be here. The eigenvector may twist around. These don't happen in a single band picture. In a single band picture, the whole vector space is one-dimensional. We have eigenvectors, all eigenvectors always in the same direction. They cannot move around. But when we have multi-band, this eigenvector can have k-dependence. They may move around. And the fact that this eigenvector may move around, then this may give you additional effect. And this effect causes a further correction to the Newton's equation. The Newton's law gets further modified because this eigenvector in the band can twisting around as you move around in the k space. Okay. And so basically, in the following, we'll just study this effect of twisting this eigenvector around. And this is another Barre's phase effect. Because remember, the Barre's phase is that we try to compare two eigenvector, nearby eigenvector, what they overlap. And we may give a Barre's phase. If these eigenvector all parallel, then they just overlap all equal to 1, so there's no effect. But when eigenvector kind of twisting around, you have to have some kind of Barre's phase. And this Barre's phase would modify the Newton's law. Yeah, so it's causing additional modification of Newton's law. And then we have a setup to really study this effect of a Barre's phase. So how Newton's law get modified when you have this additional effect. And so there's some math. So let's go through some math. Okay. Yes.
What's the interpretation of this vector, the psi alpha, the eigenvector of the m, which we got from the original Hamiltonian? Do the components correspond to probability of either one there as opposed to the other?
Very good. So let me. This is very important. So let's describe this again. So how we construct the band structure? How we get the picture of the band? We just pick a k. Okay. When you pick a k, at this particular k, you know, the k is fixed. Only it's A and B get mixed together. And how they mix together is controlled by this M. Okay. So you know, diagonalize this M matrix to obtain eigenstates. Okay, for that particular k. And this M gives us several eigenvalues. Then we get one eigenvalue here, another eigenvalue here. So we get a spectrum at this particular k. But M also gave us eigenvectors. So therefore, for this spectrum, for this eigenvalue, we get one eigenvector, which is described by this psi alpha. And here we get another eigenvector described. So this is like a eigenvector is a psi 1. This is like a psi 2. You know, alpha labeled the band. But what is the meaning of this different component? Remember, this psi alpha, this A index actually is index for the site in the unit cell. But alpha index is an index for the band. Which band? So let's say alpha equal to 1. If alpha equal to 1, this psi 1, this psi alpha equal to 1, have this psi, again, alpha equal to 1, alpha equal to 1. But A can be equal to 1 or A can be equal to 2. They have two components. For example, we have a 2 site per unit cell. So therefore, these two components of a psi actually is one for A equal to 1, another for A equal to 2. That means that when you have this particular plane wave on this particular band, you ask, what kind of weight, what is amplitude of this weight in the first site or second site in the unit cell? And these two components just describe the amplitude of this plane wave in each atom in the unit cell. For example, if this happens to be 0, that means this plane wave is very special. This plane wave only live in the second side unit cell. They don't live in the first side unit cell. So you can see how the plane wave are distributed in the two sides within unit cell. And this distribution is k-dependent. Sometimes, say here, maybe they distribute equally. And here, maybe they opposite. You know, they have different distribution. So it is because the distribution of a wave function in different sides of unit cell can vary as you're changing k. That may cause some additional effect of Newton's law. So basically, even this is like an internal structure of this particle. This internal structure twisting around as the momentum moving around. That is so actually in one of the homework problem we studied this using in the continuum. We consider a particle with a spin, and the Hamiltonian have a term that try to lock spin and momentum together. So spin always parallel to momentum. Then we have similar effect. When you're using force to push momentum around, the spin actually twisting around. And you compare a state with different spin orientations, that gives you extra barrier space term. Yeah. And so in general, in a semiconductor, when electron moving inside in the crystal, this kind of internal structure twisting around as momentum change is generically happening. It happens. So then you may have generically you have some additional effect.
Degree of freedom in my classical description picture, and then try to.
It's not quite a new degree of freedom. It's because it's locked. It's frozen. You can see for every k, this internal degree of freedom is fixed. So it's not freedom, but it's something there. As k moves, this freedom has to follow. It became a degree of freedom. We'll consider two bands together. When you jump from, if you fix k, you jump from this band to that band, you really redistribute among this side in the unit cell. So that this new degree of freedom would be liberated. But if you restrict yourself in a single band, this new degree of freedom is a slave of k. Usually, if a slave should have no effect. It's just don't do anything. It just follow the k. But this barrier space term tells us this even though it's a slave, it contributes a barrier space and modify the phase space Lagrangian. So it has dynamical effect actually. So that's why it's missed for so many years. And you know, people usually think, oh, we have degree of freedom frozen along the k, it's a slave of k, so we can drop it. We don't think about it. And then just using this picture. It's very tempting just to use that picture. It turns out that's not quite right. There's additional effect. Yeah. So it's a very good question. Yeah. Okay, so let's do it. And so here the wave packet is this. I have to fix a band index, meaning that I will consider a particular band, like a first band or second band. Let's consider a particular band. And then this wave function is this particle. It's very much like we did before. And sorry. But here's the actual term, alpha A K. Okay. So basically, without this, we get a plane wave. Okay, that's eigenstate. But here we have multi-band. To tell its eigenstate, we have to say how each side enter. What is amplitude on each side? You know. So this is a phi function. This remember alpha is fixed. So this amplitude as a function of A tell us for each side what is amplitude. We are choosing this amplitude properly. we get eigenstates and get that for that particular band. So this one really tell us which band we occupy. Okay. And the other will be same as before. We have a wave packet, we have plane wave, but we have this additional thing. So this additional thing really like the internal degree freedom. You know, if you're changing k, this one have a k dependence. So therefore, each side would enter with different amplitude as you're changing k. You can really see from here. Yeah. Okay, so let's just do it. And so I will, because of time, I will do a simpler calculation than the lecture notes. And the calculation is actually pretty straightforward. It's really just repeat what we just did. Okay, and so we have this and I d dt. Sorry. So this is the barrier phase term. So then we also have this Hamiltonian. Okay, let me calculate the easiest thing first. And this one actually is epsilon k plus phi x. Okay. Again, here I add some potential term on each side. So I add some potential term on each side. So we have a potential phi. And this calculation is exactly as before. Oh yeah, epsilon alpha, yes. Exactly as before. Okay, this is a vector. Because to calculate this average Hamiltonian for the hopping term, we assume Kc is very big, so we just drop this using the plane wave. Then we get just eigenvalue. When we're calculating the average for the potential term, we assume Kc is not so big, and potential is almost constant. So therefore, the total contribution is just a potential term at the center mass. So this is just as before. And the barrier phase term is different. Okay. So in the barrier phase term, so when we do the calculation, we want to do the, we can, for example, we can make a derivative with respect to k. If we make derivative with respect to k, we bring down an I. When we bring down an I, then average of I give us center mass. So that's how it gave us, I think gave us a minus k, sorry, gave us a minus x k dot. So this is the same as before. But however, here we have actual contribution. When you're making derivative with respect to k, in the previous case, this is only k dependence. We just bring down I. But now we have another k dependence from here. So there's an actual contribution from here. So what is this actual contribution? This actual contribution actually is given by this, so let me just write it down. This actual contribution is given by, is plus ck dot k dot. So there's an actual contribution from the k. What is ck? So let me just give it an expression, then I explain it. Ci is function of k. It's given by this psi alpha dagger k partial k psi alpha k. So here this psi alpha k is really a column vector. So psi alpha 1 is function of k, psi alpha 2 as a function of k, and etc. So this is a column vector which have a k dependence, basically. And so when you're making derivative to the column vector, we get another column vector. And this column vector have overlap with the previous column vector. Then we get some number. Oh, there's an I here. Let me see whether we have I or minus I. Yes? Yeah. Sorry. Yeah. So let me just try to get this the formula. Let me see, where is it? Yeah. So there's I here. I put I here. So there's I here. Yes?
Are you implicitly assuming that the band is non-degenerate? Seems like there would be
non-degenerate. Yeah. So just like picture, the band non-degenerate. Yeah, certainly band touch this additional complexity. We don't talk about that. Okay. Yeah. So this is how C is defined. Okay. Maybe let me do some vector. So this is the vector derivative. So this is the vector. Okay. So how we get this? And again, it's a little puzzling. You know how you get these results? Well, it's pretty messy here. Okay. But one way to look at this result, to see the result is following. To notice that this part is the orbital part. This part is internal degree freedom part. There are two parts, and they are tensor product. So what we did is to consider these two parts separately. That is, this term actually coming from orbital part, and this part is dropped. But because the internal degree part also have a k dependence, so we have this contribution from this internal degree freedom part as well. But in this case, the orbital part is dropped. So that's why the contribution from this internal degree freedom, just purely written in terms of internal degree freedom, is common vector. No orbital contribution. Yeah. And then, so this is the best way to see this. You don't need to worry about orbital part, just directly write this down. But if you don't believe this, if you don't believe what you see, you can really do the calculation. And it's a messy calculation, but you'll get same results. Yeah. Okay. And certainly there's another contribution, which is like you make a derivative respect to x. X also have a time dependence. But however, due to the same reason, you make a derivative respect to x, you bring down something I minus x, which is odd with respect to x, and this average to 0. So actually the coefficient here is 0. So nothing from x. Okay. So finally, we obtain the phase space Lagrangian for the motion of a particle inside a crystal or semiconductor. So let me just using this k x dot. Again, we kind of replace this as a k x dot up to a total derivative term of something. Okay. And then we have this actual contribution is a really minus a plus c dot k dot. And then we have this the Euro term. This is the average energy of the wave packet. It's a kinetic energy plus potential energy, basically. Okay. So what is the equation motion looks like? So once we have this, okay, let me just do one more thing. Okay. Or maybe here I don't need to do one more thing. Okay, yeah. Then once we do this, we get this equation motion. Let me say ki dot equal to minus partial phi partial xi and xi dot equal to partial epsilon partial ki. So this is equation motion we get. And this is a new term, where this d is given by this dij is a function of k, which is a partial epsilon, partial c j partial ki minus partial c I partial kj. Yeah. So basically, if you treat k as a x and treat c as a vector potential, then this is like a field strength, magnetic field strength. So the c behaves like a vector potential in the k space. And the d is a magnetic field strength in k space. It's new kind of magnetic field in k space. So that's it. We have this. And the things can be more symmetric if we can write down this. We can even write down like a dij x dot j if you want. So because I did not include the vector potential in the real space, if you include the vector potential in real space, we will have this term, this Lorentz force term. The magnetic field with this will have speed dependent force. And so this is very symmetric. And in the notes I derived this term, but here I did not derive this term. So let's just drop this term. But this term really like the magnetic field in the k space. And so the key point is that the velocity is no longer equal to partial epsilon partial k. Velocity have actual correction. They have an actual correction. And this actual correction can be also written as a force. You can see the k dot is a force. So this is a force. This basically is a force. So velocity have a force dependence. It's very interesting. There's a force dependence on the velocity. Okay, so this gave us a new kind of dynamics. And then you say, so what? You know, yeah, you have a different equation motion. Newton's law is modified. So what? Well, this is in physics. That's when you have a new effect, you ask, how do I detect this new effect? How do I observe the effect? That means what experiments do you do to observe this phenomena? If this is new phenomena, you want to see that. But to see that, you need to design experiments. So it's very important for the theory student to learn how to design experiments, although you'll never do it. But actually, it's fun. You design experiments. Hope somebody will do it, follow your design. So maybe that's a question for you. Is that we have this thing. You know, how do I design experiments to see this? Okay. So actually, in the next class, we'll discuss this. You know, what is the consequence of these new terms? It turns out that this term can give rise to so-called anomalous Hall effect. You know, usually the Hall effect is that when you have a magnetic field, then the electric field in one direction would induce current in the transverse direction. That's kind of Hall effect, which is present in the magnetic field. But however, with this term, we'll see that even without magnetic field in a semiconductor, by applying electric field in one direction, you may get currents in the cross direction, in the transverse direction, and this term have that effect. So one can using that to study this anomalous Hall effect. Okay, I will stop here. So next class we will talk about that and some topology of a band.